Okay. All right. Okay. So first of all, the homework has been extended to tomorrow deadline, that is, and we should be able to finish that, I hope. If you have any questions, let me know. Okay. So that's for the homework. Now the exam problem, I'm starting to making the second exam right now. Is I see there's going to be 4 problems, actually 3, but the first problem might be split into 2 parts, covering the irregular section, only slab, shear, and the serviceability, which is the moment of inertia for GT and cracked. Okay, so these are the content that will be covered from the exam. All right, so the exam's gonna be next Thursday, and we will fix the time for it, but most likely it's gonna be the same time frame as we did last time, the first exam, and most likely it's gonna be online. I finalize the detail with Dr. Sneed this weekend, and probably release the official information about it on Monday. But this is probably what we're looking at for the exam. Okay, and now regarding to the course content, we have covered a little bit serviceability, and there are 2 parts serviceability: a moment of inertia and the deflection. And we're going to finish moment inertia today as example, and it's going to be a short lecture today, and then we're going to continue on the deflection on Monday. All right. So before I get started, any questions about the exam and homeworks? Anything? Now's the time, or forever hold your peace. Come on. Anything? All right. Okay. So, well, apparently we're all crystal clear about the exam then. Okay. So let me continue on with the bending moment, right? With the moment of inertia. All right. So let me share my screen. And then here we go. Okay. So a quick recall what we have learned last time, right? What we have learned last time. So if you remember, we talked about several things. First, we introduced the concept, and let's just label here as lecture 23. Okay, so still serviceability, and specifically on deflection. Okay, specifically on deflection. All right, so first, we introduced the concept of I effective. I effective, right? And I effective is equal to the cracking moment MCR divided by the applying moment MA, to the power of 3 multiplied by IGT, that is transformed, plus bracket inside 1 minus MCR divided by MA, again to the power of cube, and then bracket outside multiplied by ICR. Okay, so of course you know this is transformed gross moment of inertia at stage 1, uncracked, and this is cracked elastic, and this is stage 2. Okay, this is stage 2. All right, so this is the first concept introduced, is the effective moment of inertia, So in other words, if I have a beam like this, simply supported, let me just use a different color. So simply support it, okay, and I have, for example, distribute load on it, and I see a moment just like this. Well, actually, I like to draw the moment the other way. That's how I was trained, but anyhow, this should be the moment diagram, right? So before I go on, okay, you have to be clear. Okay? So this I effective is dependent on the location. Okay? So for example, if I choose here, I call it location A, for example. This is the applied moment on the moment diagram, okay? A at A, and then you do this equation and you get a I effective at section A. Okay, can you see it? So if I say I want a I effective on position B, so I effective in position B, you take the applied moment here at location B on the moment diagram to plug in this equation. All right. In another word, this I effective is really dependent on the location, right, of the beam where you want to find the moment inertia on with. All right, so got to be careful. Got to be careful. Okay, so this is how we find effective moment inertia per one particular section for one particular section. Okay, so this is the first concept we introduced. Second concept we introduced is deflection. Oh, sorry, well, not deflection, so to speak, is the I effective for the beam. Okay, for the beam. Now this is sort of so-called average moment of inertia for a beam. Okay, so I want to differentiate these two. Okay, but before I do that, let me just go ahead and write it out. So this is 0.5 I effective at midspan plus 0.25 at its support. E1 and E2 means at support. Okay, now I want to differentiate the concept. Okay, the first one is at one particular section, at one particular section. Now the second one is average of this whole beam, of entire beam. So there are different scales and different scales. In another word, if I want to find out the middle span I effective, right? In this case, simply supported case, I will get the I effective, I'll get I effective here at midspan. Okay, I'll get the I effective here at the end. Then I do the average, and then I do the average. Okay, so if this is still confusing, let me show you, right? Let me show you, for example, for instance, right? So for instance, I have a simply supported beam, okay, just like that, okay? And I have a moment distribution like this, and I say this is 1/8 omega u L squared, all right? This is applied moment, okay? And I tell you the cracking moment is MCR. You don't have to compute it. Well, you can. It is FR, right? IG over YT, and right, remember that? But let's assume this is known, okay? Assume this is known, all right? And then what we do is, let's find IE middle span. Okay, in this case, IE middle span, I'm going to use this equation 1. Okay, this is equation 2. I'm going to use equation 1 here to find middle span. Okay, so for middle span, MCR is this fellow here. MA is 1/8 omega UL squared. Can you see it? And this is 3 multiplied by IGT plus bracket inside 1 minus MCR divided by MA, which is 1/8 omega UL squared cube and ICR. And that's it for middle span. Okay, for the support, okay, since it's symmetric, for the support IE1 equal to IE2, that is MCR divided by what this matter. This is applied moment. Applied moment. You notice that at the end of it, the applied moment is 0. Okay, applied moment is 0. Sorry, this is MCR divided by 0 cube and ICR. Right? So once 0, this goes to infinity, isn't it? Okay, so we don't have a rational number. For this case, we just let IE1 equal to IE2 equal to IE middle. Okay, this is for simply supported case. Then the effective, right, IE would equal to 0.5 of IE middle plus 0.25 of IE1 plus IE2. Now, given we know that IE1 equal to IE2 equal to IE middle, this is basically 2 IE middle. So IE equal to this is 0.5, this is 0.5 multiplied by 2, so 0.5 again, this is basically that. Okay. So the reason why I want to show you that is see that, it doesn't make any sense to carry out the calculation for I effective for simply supported beam, because the effective moment inertia for simply supported beam equal to the effective moment inertia of its middle span, because there's no moment at two supports. All right. So equation 2, this equation fellow here, applies, okay, applies only to continuous support. Okay, only applies to continuous support. If it's simply supported case, it doesn't matter. It doesn't help. Okay, you just not need it. You do not need it. You do not need it. Okay, all right. So this is just more of an illustration on how to use these two equations. On how to use these two equations. Okay, all right, folks. Any questions on this? Any questions on this, guys? Are we clear? Are we clear? Anything? Quiet, silent, falling asleep? All right, okay. Well, this is simple, right? This is pretty simple, okay? So I'm gonna demonstrate in the little more involved case, okay? So let's go back to our last lecture's example. Right? So remember last lecture, we show you a beam, right? We show you a beam, and this is the column and beam joint. Remember, it's a column and beam joint. Okay. You know what? Let me use the blue color so I can use the rebar in a different color. Sorry about that. Compose the behavior. So here, that's the column and that's the beam. Column again, a beam, and column, sorry, beam, column, beam, column, beam. Okay, and we mentioned that there are reinforcement, right? So reinforcement here, the bottom, I have a one very long layout, and this is two number 8 bars. Now on top of that, I have two number 9 bars. Okay, and on the compression side or at the support, and the support is tension side, right? And this is 4 number 9 plus 1 number 11, and this is the same thing, 1 number 9, so 4 number 9 and 1 number 11. Okay, all right, so these are the configurations, and then we also mentioned that the clear span between inside of the column is 25 feet, and from center to center is 26 feet. Center, 26 feet. Okay, all right, so this is the geometry that we talked about last time, right? This is geometry we talked about last time. And we also show you the moment diagram. The moment diagram looks like this. So I have a support, so clear support to support. Okay, and the moment diagram, you just go ahead and use red. Okay, so this is the moment diagram. Looks like just like this. Okay, and here is minus 225 kip foot, a negative bending moment, kip foot. And I have a peak moment here of 162 kip foot. 162 kip foot. Okay, so you notice this is continuous support. This is continuous support. So from the moment diagram, I do have negative moment two ends. That means I see this, I immediately realize that I need to find my I effective middle span and also my IE1 and also my IE2. Okay, and I'm going to use that effective equation for moment inertia equal to 0.5 I middle span, so 0.5 IE middle plus 0.25 IE1 plus IE2. Okay, all right, so you ask, why do I need IE anyway? Because we need to calculate deflection, which we'll talk about Monday, okay? But for now, let's just say we need to find out the effective moment of inertia across the span, okay? So how to do that? Right? So now let's take a look at the section of the beam, right? So far, I haven't shown you the cross section, right? So first of all, let's show you the cross section. The cross section is a T-beam. So T-beam cross section. Okay, so what it looks like, right? What it looks like is this. Okay, so I have a T, nice T. Okay, and then I have a flange width of 75 inches. Okay, and I have a height of the flange of 5 inches. Width of it 14. Okay, and I have a total distance between top and bottom, that is 24.5 inches. Okay, and this is my cross section. And to make it easier for us, okay, I'm going to label the neutral axis right here. Okay, and I tell you that this distance right here is 7.66 inches. But note that this is for positive bending moment first, right? Okay, now the center does not change if you flip it, but we're looking at a positive bending first, okay? So first of all, we're looking at is positive bending. So I, G, T for positive bending moment. So why? Why positive bending moment? Because right here, this in the middle span, this is positive bending moment. And at the end support, this is negative bending moment. Okay, so they're different. So we're first has to find out this IE middle span. And remember IE middle equal to what? Equal to MCR divided by MA to the cube multiplied by IGT plus bracket inside 1 minus MCR divided by MA to the cube and bracket inside ICR, right? So here in this equation is if you were to find IE middle span, you need the IGT, you need ICR, okay? And both IGT ICR is at the positive bending, okay? Positive bending or negative bending, depends, right? Here in this is middle span, so it is positive bending. Since it's the middle span, so it's positive bending. So we're going to find out IGT, ICR for positive bending first. That's what we're doing here, okay? That's what we're doing here. All right, so to find out the positive bending, right? Positive bending, I already have this cross section, I have the neutral axis, and you know how to find moment inertia, right? For IGT. So for IGT, right? For now, let's just ignore the reinforcement. To make our job a little bit easier, okay? Ignore reinforcement for now, okay? And I can calculate IG equal to IGT approximately equal to IG, means just consider the section that equal to 33160 inch to the power of 4. To the power of 4. Okay, all right, so this is IGT approximately equal to IG equal to 33164 inch to the power of 4. This is for positive bending, okay? Now, quick thinking here. If I convert everything back to negative bending moment, right? So for negative bending moment, again, if I ignore the reinforcement, it doesn't really change, does it? So if this is positive, this is negative, right? It's the same thing. Okay, now I can do this because I ignore the reinforcement. All right, I ignore reinforcement. So for the uncracked cross section, it is same in terms of positive bending or negative bending. Okay. All right, so this is easy, right? This is easy. For positive and negative bending moment, I end up with the same moment of inertia. How about for cracking? Right? So next step is, what about ICR? Okay, what about ICR? So first of all, also for positive moment. Okay, for positive moment. Now, the issue here is that when I talk about ICR, that is correct. That is correct. Meaning the reinforcement cannot be ignored. Reinforcement cannot be ignored. Okay, so if the reinforcement cannot be ignored, then ICR positive does not equal to ICR negative. Okay, why? This is why, right? So for example, the positive bending, right? Again, positive bending moment. I'm just going to short here, positive bending moment. Let's draw the section. So the section looks like this. Nice looking T section. Okay, and then let me use red. to label the effective compressive zone, right? And assume the effective compressive zone is within the flange. Okay, assumes within the flange, and I can actually calculate the compressive zone size KD. That is equal to 3.73 inches, smaller than 5 inches. Okay, smaller than 5 inches. And also, I know that the tensile reinforcement after conversion, this is N multiplied by AS, okay? And this will crash, so there's no -1, right? So 8 times N ES over EC, approximately equal to 8, right? 8 times of 2 number 9, 2 inch square number 9, plus 2 number 8, so 0.79 inches, number 8 multiplied by 2, okay? So I have this total to be 28.64 inch squared, okay? And to give you some location, right? Give you some location. This is given. This is given. The heights or the depth of the reinforcement is 22 inches. The concrete cover is 22.5 inches. Okay. All right. So this is the positive bending moment. Positive bending moment. Okay. Just save the time so you can go ahead and compute the moment inertia, which I will show later. But for negative, quickly, for negative, it is different. It is different. Why different? Because now same cross section, okay? If it's negative bending moment, my compression zone is going to be within the web, okay? My compression zone is going to be in the web. So I use that equation and turned out KD, this height here, KD, equal to a 8.65 inches. Okay, 8.65 inches. And I convert the reinforcement here. Okay, and this is now AS prime. So this is N minus 1 AS. Okay, so A minus 1 multiplied by a 1.58 inches squared. Okay, and this roughly equal to 11.06 inch squared. Okay, all right, so this is the compressive reinforcement. Now you notice that here, this is 1.58 inch squared. And I have 1.5 inch. What happened to that 2 number 9 bar? What happened to the 2 number 9 bar, right? So why I did not have the 2 number 9 bar here? That is because if you take a look at the moment diagram here, when I say negative bending moment is right here, right? For negative bending moment. And for negative bending moment, right? This is for the negative bending moment. This is for the negative bending moment. Okay, so for the negative bending moment, it is only this longitudinal bar here pick up the compression. Okay, the 2 number 9 is too short. The 2 number 9 is only for positive. Okay, this is only for positive. Okay, why? Because it terminates here. It does not go all the way across. Okay, so I did not incorporate that 2 number 9 bar in the area conversion here. Okay, I did not. All right, then the top part is the tension. Okay, so this is the tension side of it, tension. And this equal to NAS, and that is 8 times multiplied by AS, which is 4 number 9 bars, so 4 multiplied by 1 inch squared, plus 1 number 11 bars, right? So it's 1.56 inch squared. This is 1 number 11 bars. Okay, and I have this to be 44.48 inch squared. Okay, all right. So this is the negative section, okay, negative section. All right. So you see, it's a little bit different. It's a little bit different. Okay, when you calculate ICR for positive, ICR for negative, they're a little bit different. Okay, all right. So now I have my negative and positive crack moment calculated, right? I need to move on, right? I need to move on to calculate my effective moment of inertia, effective moment inertia. Okay, so I'm gonna go ahead calculate I middle, so IE middle span, right? In other words, this is for positive moment. Okay, positive moment, my middle span, right? So that equal to MCR divided by MA, bracket outside, 3 Ig plus bracket inside 1 minus MCR divided by MA power of 3 bracket outside ICR. Okay, this is the equation I'm going to use, right? So I need to find my cracking moment first, right? So MCR equal to FR modulus of rupture multiplied by Ig divided by YT. Okay, the distance between the neutral axis to the tensile side of it, Okay, so I just want to bring the number in. So 7.5, concrete strength of 4,000 psi of concrete. And then here for the Ig, that is 33160. I computed already. And then this is inch 4, don't forget. Divided by 24.5 inch, this is essentially the depth. Okay, minus 7.66, this is Y top. Right, then I get the YT. Okay, so after the after the computation, I have a number of 78 kip foot. This is the cracking moment. This is cracking moment. Okay, now what is the apply moment, MA? Notice that this is the positive bending moment, right? And from the moment diagram, sorry for scrolling up, but from the moment diagram is 162 and is positive. So MA here at middle span is 162 kip foot. Positive. All right. So quickly, MCR divided by MA equal to 78 divided by 162. What I have here is 0.481. 0.481 ratio. Okay. Now, in case I did not write ICR for positive bending moment here, ICR, I pre-computed, that is 10860 inch to the 4. This is positive, and ICR negative is, let me see what I get, this number is 11366 inch to the power of 4, okay, just to save time, okay, just to save time. All right, these are different. So I can use that number, which is ICR positive is, what is this again? ICR positive is 10860 inch to the power of 4. So I bring back to this equation right here, okay? So IE at the middle, then equal to a 0.481, that's the ratio here, to the power of 3, multiplied by IG. What is IG? IG is 33160 inch to the 4. So 33160 inch to the 4 plus bracket inside 1 minus 0.481 cube. Outside ICR is 10860 inch to the 4. Okay. All right. So I run this calculation and I can find out my IE essentially equal to a number of 13340 inch to the 4. Okay, so this is the effective moment of inertia at the middle span. Okay, all right. How about at the support? How about the support? Recall the moment diagram, right? Recall the moment diagram, right? So this is the beam, and the moment diagram looks just like this, right? So we just calculate here 162. How about 225? Right? How about 225? Okay, so this is IE1, IE2 that we're talking about. All right, so for IE1, right, we need to compute the same thing again, right? Some parameter changes. For example, the cracking moment MCR for a negative bending moment at this section here is different from the positive. Why so? Because I need to do the FR, IG stay the same, but remember YT changes. Okay, YT changes because in this case, I'm looking at 7.5 4,000 PSI multiplied by IG, which is YG negative. It is, wait, IG 33160 divided by a YT here. What is YT? 12.25 inches. 12.25 inches. Okay, so I'm going to proceed and do this calculation. But one thing I suddenly realized, one thing I suddenly realized, this IG here, well, I said previously, right? The positive and negative bending are the same because, you know, if I do the negative, I'm going to look like this, right? And this is still neutral axis. This is for negative, right? I just need a compression and the tension and goes on and like that, right? Right? This would be my understanding of IG for the negative side of it, right? For the negative side of it. However, ACI has exception. ACI says no. Okay, you cannot do that anymore. Cannot do that anymore. Okay, so for the negative bending moment, and this is for negative bending moment. Okay, negative bending moment, IG positive does not equal to IG negative anymore by ACI. Okay, sorry folks, but that's the ACI rule. Okay, so if it does not equal what it is, right? So ACI says, okay, if you want to flip the section like this, so you have to treat it as a rectangular. Okay, means ignore tension from the flange. You cannot consider tension from flange. Okay, you have to ignore the tension from the flange. So if I ignore it, this is the B width, that is 14 inches. Okay, and the height is 24.5. So if I ignore the wings, so IG negative, that is 1 over 12 BH cubed, so equal to 1 over 12 multiplied by 14 inches multiplied by 24.5 inches to the power of 3. All right, so that means cannot use this anymore. Instead, you use this number. That is, what is this number? 17200 inch 4. So 17200, right? Extra 0 is not helping, so inch to the 4. Okay. So a little bit trick here. Got to be careful. Okay. All right. So now this is for T. Okay. If you have for a rectangular section, you wouldn't have the problem like this. Okay. Only for T and for I section, you cannot use the tension developed from the flange. That's just by ACI. All right. Okay. So correct all these numbers, right? And don't forget the tension side now, this is Y top, basically, equal to the YT. Okay, equal to 12.25 inches. All right, so MCR minus, I bring all the number in, I got a calculation done, which is 55.5 kip foot. Now that is the negative cracking moment. All right, so I have negative cracking moment. What is my applied negative moment? That is minus 225 and, oh, sorry. This is negative 225 kip foot. Negative 225 kip foot. Okay, so this is the cracking moment. So let's put a negative sign in front of it. Okay, let's put a negative sign in front of it. Okay, why is that? Because I want to have MCR negative over MA negative that equal to a 55.5 divided by 225. What's the ratio here? Let me see, 0.247. Now the negative sign cancel each other. Negative signs cancel each other. Okay, so now I can use IE1. Okay, in this case, be careful since I have a moment M1 equal to M2, so I can say that IE1 equal to IE2. Okay, but if the moment is different, you cannot say that. But in this case, got lucky they're the same, so I can use the same. So use that equation is 0.5 multiply, sorry, not 0.5. It's the, remember, MCR minus MA minus cube multiplied by IG minus plus 1 minus MCR negative divided by MA negative to the cube power, sorry, to the cube, and then ICR negative. All in negative. All in negative. All right. So I can proceed with this one, and this is 0.247 to the cube, and IG negative, it is 17200 inch to the 4, and plus this fellow here equal to a 1 minus 0.247 to the cube, and ICR negative is 11366 inch to the 4, and then I end up with 11450 inch to the 4. All right, so this is my IE1, IE2. Okay, why am I going this length to get all these numbers? Because I need my effective moment of inertia equal to 0.5 IE middle plus 0.25 IE1 plus IE2. Right? So now what is this value here? This is basically the positive, this is negative, this is negative, right? So I have obtained my IE middle here, 13340. So 0.5 multiply 13340 inch to the 4 plus 0.25 multiplied by this number, so 2, because they're identical, multiply 11450 inch to the 4. Okay, and do the calculation. I find out this 12395 inch to the 4. Inch to the 4. Okay, what does this number mean? Now I finally took so much effort, right? It took me about like 30, good half an hour to arrive at this answer. What does this mean? It means now for a beam that has a moment diagram like this, 162 of positive bending, negative 225 of negative bending. For a beam as a moment diagram like this, I am going to use I effective equal to 12395 inch 4 to determine deflection. Okay, to determine deflection. And what is the equation for it? What is the equation for it? Turned out the deflection equation for this continuous beam, for this case, delta I dead load plus live load has equation given to you, okay? And this is 5 over 48 multiplied by L squared, and L is the span length EI. Here, notice this EI is this fellow right here, okay? EI here, and then N moment, middle span moment, plus 10% 1.0, sorry, 0.1, the end moment, M1, which is M1, M2, so this is, okay, right, okay, so this is the equation to calculate the deflection at middle span, and this is deflection at middle span, okay? All right, now don't worry about this equation yet, because we're going to talk about it next lecture, but you see, this is how we're going to use the calculated moment inertia to get the deflection. And all this effort is just to get effective moment inertia. This is all this effort is just to get effective moment of inertia. Okay, all this, including previous lectures content. Okay, so just quick review, right? Essentially, what we're doing is we're going to use this equation to find out the effective moment inertia for particular section. When we say particular section, normally it means at the middle span and at ends, at end constraints, right? And after we get the effective moment inertia at middle span and the two ends, we compute the effective moment inertia combining these two and use that to calculate the deflection for that beam. So that is the thought process. That is the thought process. Okay. All right. I think this is a good point to stop. So any question from you guys? Any questions, guys? A lot of information to digest, okay? Thursday afternoon, we're all falling asleep, but a lot of information to digest, okay? Now, this part, I don't think we'll incorporate that in the second exam. I don't think we'll incorporate that into the second exam. But if we do, I'll tell you guys on Monday, okay? If we do, I'll tell you guys on Monday. All right. So any questions? Dead silent. All right. So let me just stop recording.